Welcome. In this session, we'll begin to explore level curves. Level curves are a way for us to visualize functions that have vector arguments. We'll want to visualize things, and the level curves are also useful when we try to understand the gradient one-forms. So what we'll do first is we'll define them. So we will define a level curve of, so this is a function that maps a vector to a real number, or we might write that as a function that has a vector argument, and we'll say that that's at level, we'll use script L, and we'll say that that is the set, and we'll put a subscript C to indicate curve. Later we'll use a different little symbol, but this will be subscript S, script S, subscript C, and this is a function and a level, and we will define this as the set of all vectors in the vector space such that when we take that U vector as the argument of F, it's at level L. So this is a slightly complicated definition, but the idea basically is that this is also called a contour of F at that level. And if you've seen contour maps, for example, topographical maps of an area where you might want to go hiking, a contour map is a group of level curves. And as we go, for example, up a mountain, those contours get more and more circular and more and closer to a point. And then as we get down into a valley, those contours turn into usually parallel curves that go along, for example, the edges of a river. So they have many properties. So let's stop here with the definitions and let's switch to some computer-generated slides so that we can take a look at what these level curves are. First, to understand a level curve, let's look at a linear function. And a linear function is a linear form with a scalar offset. So let's suppose that we have function 1, and that's this one form times our vector argument minus 2. Well, what does that look like? Well, what we'll do is we'll plot three things. We'll plot this as a 3D surface, we'll plot it as contours, and then we'll add in the transpose of the gradient so that you can start to see how the gradient comes into these contours. So what this does is, this is the 3D plot of the values of F. So the values of F will increase as we increase W2. They'll decrease as we increase W1. And then there will be a constant offset of 2 in this plot. The contours of this will look like parallel lines, and in particular, the gradient at any point is going to be, if we differentiate this, we'll see that the gradient of this function is the gradient of this linear form minus a constant, so the gradient will just be that one form, and that if we transpose that one form into a vector, what it's doing is it's giving us a perpendicular or a normal, and we're seeing that every contour of this linear function is perpendicular or orthogonal or normal, all the same word, all the same meaning in 2D. They're all perpendicular or normal or orthogonal to the transpose of that one form. Now, let's take a look at something a little more complicated. Let's take a look at a quadratic function. So a quadratic function, in this case, they get more complicated, but here, what we're doing is we're taking our vector argument and we're offsetting by some constant g. So g is going to be a center of some kind. And this is symmetric, and we're sort of inserting, you can imagine that there's a B in here, a B matrix that's symmetric, and it's the identity. So now let's try plotting the surface and the contours. So what this looks like is, this looks like, it's called a paraboloid. So it's a rotation. So it's called a surface of revolution, and what that means is that at any level, so each level curve of this is a circle. Well, let's verify that. Yes, when we plot the contours of this, or the level curves, what we're seeing is each of the level curves is a circle, and they all are centered at that vector g. What is the transpose of the gradient for these? Well, the transpose of the gradient is always perpendicular to the contours, or to the level curves. And that is going to happen in general. We won't prove that, but it's a fact that we're going to use. Now, let's take a really complicated function. Here, there's a function that's built into MATLAB, and I want to use that function to illustrate some of the things that we have. Another term for this function is a Gaussian mixture model. So this is a quite complicated function, and when I plot it, this is what I'm seeing. Each of these is a Gaussian curve in 2 dimensions. So there's a peak here, and there's a peak here, and there's a valley here. So that's the way that and there's another valley over here. So that's the way I've set it up. Let's take a look at the contours. Well, the contours are showing us a little bit more information now, because here, that's corresponding to one peak, and then that's corresponding to a valley. And we're not sure what these others are. We'd have to, in order to better understand this function, what we'd really like to do is we'd like to have the surface plot and the level curves available to us at the same time. And I'll draw attention to a few things that are features of this plot. One is that these zones here are places where we're going from peaks to valleys. At this particular one, what's happening is these contours are coming extremely close to each other. So the level curves are very close to intersecting, and here they actually do intersect. And what we'll understand much later in this course is that these places are corresponding to local maxima and minima of a function that has a vector argument. And these points, for example, are corresponding to saddle points of the functions.